Okay, so in this particular question, we've been presented with an unidentified compound, and we've been told the percentage composition by mass of the various elements which make up the compound. So in this case, we've got sodium, sulfur, and oxygen, and we've been asked to work out, okay, well, what is the actual empirical formula of this compound, right? So how am I going to approach this? What's one of the first things I'm going to have a go at doing, and where am I going to go from there? So the first thing I'm actually going to do is I'm going to add up the percentages just to have a look at what I get, right? So if you have a go at that, see what you come up with. But so I've got 29.08 plus 40.58 plus 30.34 right? Now, if you do have a go at working that out, what you should come up with is that comes to 100, right? And in this case, we're dealing with percentages, so I would represent that as 100%, okay? The next thing I'm going to try and do, because what I want to be able to do is compare the elements, right? I want to be able to compare their quantities, but what we've got here is percentages by mass. It's not very easy to compare them because they have different molar masses. They have different, relative atomic masses, each of them. So I need to convert it first into a format that enables me to really compare the actual amount of them, rather than trying to compare the mass, which is not exactly directly helpful. Okay, so in order to do that, how am I going to get it to a state where I can compare the actual amount of each? Well, I'm going to do that through trying to work out the moles, right? So the amount of substance, and I'm going to use the moles equals mass divided by molar mass equation to do that, right? So that's in grams, that's in grams per mole. Okay, so where are our molar masses? Like, how do we work that out? Well, we need the periodic table. I mean, unless you've kind of memorized what the relative atomic masses of all of these are. But if we do refer to the periodic table, remember we're looking for sodium, sulfur, and oxygen. As you can see, we've got sodium, that's going to be 23. So these are the MRs, right? So Na is going to be 23. For sulfur, that's going to be 32.1. And for oxygen, that's going to be 16, right? Okay, so now that we've got those numbers, we need masses to work with. So we're going to make an assumption which is going to help us to move this forward towards achieving our goal of determining the empirical formula. The assumption I'm going to make is I'm going to assume that I have a sample of this compound, and that particular sample of this compound has a total mass of 100 grams, and that's going to make the sample, or it's going to make the compound much easier to run calculations with. Okay, so if we make that assumption, what does that mean for these numbers? Well, it means that effectively these can be converted into masses, right? So you can imagine that would be therefore 29.08 grams. So that's with the Na. For the sulfur, that's 40.58 grams. And for the oxygen, right, 30.34 grams. Okay. Beyond that, we're going to now take our molar masses and we're going to use those to work out the moles, right? So in this case, the moles, I'm just going to put an n here, and the moles are going to be these values divided by their respective molar masses. And what if we do that, what's that going to give us? Well, here this would be 23. Here this is going to be 32.1, and here this is going to be 16, right? Okay, so I would invite you to see what you get when you actually run these calculations for each of those, and we're just going to write this out as though now it's a ratio, because that's effectively what we've established. We've established a ratio between the sodium, sulfur, and oxygen. And so if you do work these out, what you should get, and I'm going to write these to 5 decimal places, what you should get is for sodium 1.26435. For sulfur, right, we're going to get 1.26417. And for oxygen, what are we going to get? Well, for oxygen, we're going to get 1.89625. Right. So this is the ratio that we've currently just established, and we do need to try and get this to calculate our to get to our empirical formula. We need to get this to a whole number ratio, and we need to get to the simplest whole number ratio, right? So what would be our next step? Well, one of the fastest ways to establish at least one whole number here is to divide all of them by the smallest value, right? So in this case, the smallest molar value in this kind of ratio we've established is that of sulfur, right? So that's 1.26417. So what I'm going to do is I'm actually going to divide all of them by 1.26417. So let's just do that. And when we've done that, what are we going to get, right? Well, if we do that, at this stage, I would invite you to have a go, see what values you get, and have a think about what the implications are and what the next steps after that might be. But okay, if you do that, what you should get for, in the case of the sodium, is 1.00 Okay, I'm trying not to erase the ratio symbol, but okay, that's not, it's happening a bit too slow. Okay, there we go. Yeah, so 1.00 14, right? For the sodium, no, not sodium, yeah, sulfur. For the sulfur, I looked at the S and I thought, okay, for the sulfur, we're dividing the number by itself. We do not need a calculator to work that out, right? So, I mean, that's just going to give us 1, right? And for the oxygen, well, if you work that out, what you should get is, and in the first instance, I'm actually going to write it first of all over here to 6 significant, to 6 decimal places, and then I'm going to convert it to 5 decimal places, just so you see the contrast, right? So when we write it to 6 decimal places, we're going to have 1.4999996, right? So this is what it is to 6 decimal places, and we're going to, for the purposes of this, we're going to round it to 5 decimal places. And when we do that rounding to 5 decimal places, we're simply going to get 1.5000. Okay, so I'm going to just add this here, so 1.5000. So at the moment, what we can see just from visual inspection is that, first of all, if we look over at the ratio, if we look at the moles corresponding to the sodium here, this is a whole number. Now, I may have just said sodium, I meant sulfur, but I'm not sure. So anyway, for the sulfur, it's 1. For the sodium, it's very close to 1, but it's not 1. But for all intents and purposes, what we're actually working with here, if we round this to 3 decimal places, it's 1. If you round it to, and so on and so on. If you round it to 2 decimal places, it's 1. If you round it to 1 decimal place, it's 1. It's close enough to 1 that if we round it for the purposes of what we're working with here, it's basically 1, right? I'm going to keep it the way it is for now. We can do any rounding later, but it's more or less 1. So what we're really worried about is actually the oxygen, right? Because that's 1.5. It's not, we can't say that it's super close to being an integer, right? So it's 1.5. So, but now let's consider scaling up. So we want to get that oxygen, especially to be a whole number, right? So how do we scale this up? So the way I'm going to scale this up, so you would consider, okay, well, maybe multiplying it by 2, multiplying it by 3, multiplying it by 4, multiplying it by 5, and the first number you come across in that scale up process that gets it to the simplest whole number, you kind of stop there and, okay, there we've achieved it. In this case, simply just by looking at it, you can kind of figure that, well, if I multiply 1.5 by 2, we're going to get a whole number, right? You're going to get 3, right? So let's do that, right? So let's multiply everything by 2. So this is what we're going to do at this stage. Multiply everything by 2, right? And what do we get? So here we're going to get 2.00028. Here we're going to get 2, right? And here we multiply that by 2. What are we going to get? We're going to get 3, basically, right? And if we now, because of what I've already explained, this is already so close to being a whole number. If you literally round it to even 2 decimal places, it's a whole number. It's 2, right? So effectively, if we do the rounding at this stage, even, as I said, even to 2 decimal places, for example, you've got 2.00 to 2 to 3, right? Which is more or less like, well, you can see that that's just 2 to 2 to 3. So we now have a whole number ratio between them. Is it our simplest whole number ratio? Well, if we divide 3 by, anything other than really, like at this stage, maybe divide it by 1, which is not going to do anything, right? So it's just going to give us 3. We're going to get a non-integer number somewhere in our ratio. Like, for example, if I divided it by 3, we're going to get numbers here which are not whole numbers, right? So this is our simplest whole number ratio. This is what I can kind of safely conclude at this point. And therefore, as you can imagine, therefore they would be associated with the sodium would be a 2. So the sodium would anticipate a 2 would be associated with the sulfur. We anticipate again a 2 associated with the oxygen. We'd anticipate here we used to see a 3 associated. So therefore, what we're getting out of this, we're going to get Na2S2O3. And so now what we have is the form where we have the simplest whole number ratio between the values. In other words, we have our empirical formula.